Hello, and welcome to Sleep Archive. When we walk into a quiet forest, we are completely deceived by our own perception of time. To human eyes, a towering redwood or a sprawling oak appears as a static, peaceful monument of nature. We view them as permanent, silent fixtures of the landscape. But this tranquility is an absolute illusion, born entirely from our fast-paced metabolism. If we were to speed up the flow of time and peer beneath the thick, grooved bark, we would not see a quiet, passive organism. We would see a violently active, heavily fortified industrial complex. A fully grown tree is one of the most mechanically complex biological machines on the planet. It is a towering fortress that spends its entire existence locked in a ruthless, physical war against gravity, extreme weather, and microscopic invaders. To survive, it must operate a sprawling network of high-tension plumbing, subterranean chemical refineries, localized defensive artillery, and microscopic solar forges. It must pump thousands of gallons of heavy liquid straight up into the sky without a moving mechanical heart. It must forge invisible atmospheric gas into solid structural armor, and it must do all of this while remaining permanently bolted to a single square yard of earth. This is not a passive plant. This is a masterclass in autonomous, brutalist biological engineering. This is the architecture of the fortress. To truly understand the mechanical triumph of a tree, we must first address the sheer physical impossibility of its architecture. If a human engineer is tasked with building a skyscraper, they rely on a deep foundation and a rigid, internal skeleton of forged steel. The heavy steel beams provide the necessary tensile and compressive strength to hold the massive weight of the building upright against the crushing force of gravity. In the animal kingdom, biology solves this exact same problem by using an internal scaffolding of dense, calcium-rich bone. A tree possesses neither steel nor bone. It has absolutely no central skeleton to hold itself up. Yet, it can grow to be over 300 feet tall and weigh upwards of 2,000 tons. How does a biological organism build a multi-ton skyscraper without a skeleton? The answer lies in microscopic cellular engineering. If you examine a human cell, it is essentially a soft, squishy balloon filled with water and proteins. It is highly flexible, but it has absolutely no structural integrity on its own. If you stack 1 billion human cells on top of one another, they simply collapse into a puddle. A plant cell is built entirely differently. The living, fluid part of the cell is not exposed to the outside world. Instead, the plant cell physically encases itself inside a rigid, geometric box. This box is the cell wall, and it is forged from a complex biological polymer called cellulose. Cellulose is incredibly strong. At a microscopic level, it is woven together into dense, intersecting microfibrils, acting much like the fiberglass used to build the hulls of modern boats. But a rigid box alone is not enough to build a towering skyscraper. An empty cardboard box will eventually crush under heavy weight. To turn this microscopic box into a structural, load-bearing brick, the plant uses a physical mechanism called turgor pressure. Deep inside the plant cell is a massive, hollow storage tank called the central vacuole. The cell actively pumps salts and sugars into this tank. Because of the inescapable laws of osmosis, surrounding water violently rushes into the vacuole to balance the chemical concentration. As the tank fills with water, it physically expands, pushing outward against the fluid cytoplasm, which in turn violently pushes against the inside of the rigid cellulose wall. The cell becomes incredibly pressurized, much like a heavily overinflated car tire. The water physically cannot escape, and the rigid cellulose wall physically refuses to burst. This traps the water in a state of immense hydrostatic tension. The microscopic, squishy biological cell has suddenly been transformed into a hardened, highly pressurized structural brick. When you multiply this localized hydrostatic pressure by trillions of individual cells, the cumulative physical force is staggering. This collective turgor pressure is the exact mechanical engine that allows a tiny, fragile green sapling to physically shatter a concrete sidewalk and stand upright against the wind. However, as the tree grows from a small sapling into a massive multi-ton skyscraper, relying purely on water pressure becomes mathematically and structurally impossible. If a severe drought occurs and the tree loses its internal water pressure, a 300-foot tower made entirely of pressurized cells would catastrophically buckle and collapse under its own colossal weight. To bridge the gap between a flexible green plant and a towering fortress, the tree must completely abandon the concept of living support. It must build its skyscraper out of the dead. Just beneath the bark of the tree lies a microscopically thin, continuous ring of living tissue known as the cambium. The cambium acts as an automated, biological 3D printer. Its sole purpose is to endlessly divide and print new cells. But as these new cells are printed and pushed inward toward the center of the trunk, they do not remain soft. The tree forcefully injects their cellulose walls with a heavy, concrete-like chemical called lignin. Once the walls are fully reinforced and heavily lignified, the tree intentionally cuts off the nutrient supply. The living cells inside violently die, dissolve, and are flushed away. All that remains are the perfectly preserved, interlocking, heavily armored cell walls. This dead, lignified tissue is what we call wood. Year after year, the living cambium printer wraps a brand new, solid ring of this dead armor around the core of the tree, constantly widening the base and pushing the structure higher into the atmosphere. The most vital load-bearing pillars of the biological skyscraper are entirely composed of microscopic corpses. The tree literally builds its towering skeleton out of its own dead tissue, forging a fortress so structurally sound that it can withstand the physical assault of century-long storms. The towering wooden skeleton of the tree provides the physical architecture necessary to reach the upper atmosphere, but a skeleton alone cannot sustain a living organism. To maintain its sprawling root systems, manufacture its chemical defenses, and continuously print new rings of solid wood, the tree requires an astronomical amount of energy. In the animal kingdom, organisms acquire energy by physically consuming other life forms and breaking down their chemical bonds in a highly acidic stomach. The tree does not hunt, and it does not possess a digestive tract. Instead, it pulls its energy directly from the vacuum of space. Every single leaf on the canopy is not just a piece of green tissue. It is a highly engineered, microscopic solar panel designed to capture ambient radiation from the sun and physically convert it into solid, structural mass. This is the mechanical engine of photosynthesis, and it operates on a level of quantum physics that human solar technology has yet to perfectly replicate. If you peel back the waxy, transparent outer cuticle of a leaf and zoom deep into the internal cellular matrix, you enter the mesophyll layer. Here, the cells are absolutely packed with thousands of microscopic, disc-shaped organelles called chloroplasts. These are the localized solar forges. Inside each chloroplast is an even smaller, highly complex architectural structure called a thylakoid. The thylakoid is essentially a sealed, fluid-filled biological envelope, and embedded directly into its outer membrane are dense clusters of pigment molecules, primarily chlorophyll. Chlorophyll is a masterpiece of thermodynamic engineering. It is a heavy, ring-shaped molecule designed specifically to intercept the physical impact of a photon. When a photon, a massless particle of pure light energy traveling 93 million miles from the sun, violently slams into the leaf, it penetrates the chloroplast and strikes the chlorophyll molecule. The kinetic energy of this cosmic collision is instantly absorbed by the pigment. This absorption causes a violent, physical reaction within the chlorophyll. The energy excites an electron within the molecule to a highly unstable state, physically ejecting it from the pigment. The solar panel has successfully generated a microscopic electrical current, but a loose electron is incredibly volatile and dangerous to the cellular machinery. To harness this raw electrical energy, the chloroplast must immediately pass the electron down a highly organized biological conveyor belt known as the electron transport chain. As the electron is forcefully bounced from one embedded protein to the next along the thylakoid membrane, its kinetic energy is systematically siphoned off. This stolen energy is used to power a microscopic, mechanical pump. This biological pump forcefully drives loose hydrogen ions, protons across the membrane, packing them tightly inside the sealed thylakoid envelope. Just like the highly pressurized water inside the plant cell, this creates immense physical tension. The protons fiercely repel one another and scream to escape the microscopic pressure cooker. When the pressure reaches a critical threshold, the protons are allowed to violently rush back out, but only through a single, specialized exhaust valve called ATP synthase. ATP synthase is not a metaphor. It is a literal, microscopic rotary engine. As the pressurized protons blast through the valve, they physically force the internal protein shaft of the engine to spin at staggering speeds. This mechanical rotation acts as a biological alternator, actively hammering loose phosphates onto molecules to forge ATP, the universal energy currency of the cell. However, the tree has a physical problem. When the chlorophyll violently ejects its excited electron, the pigment is left dangerously unstable. To reset the solar panel for the next photon strike, it must instantly find a replacement electron. To get it, the chloroplast executes a brutal chemical theft. Using the raw, localized energy of the sun, the chloroplast grabs a molecule of water drawn all the way up from the roots and physically tears it apart. It violently rips the hydrogen atoms away from the oxygen atom, stealing their electrons to replenish the chlorophyll. The shattered, discarded oxygen atoms immediately bond together and are expelled out of the leaf as waste gas. Every breath of oxygen in the Earth's atmosphere is the direct, toxic exhaust of this microscopic, violent, watery demolition. With the raw solar energy successfully trapped in the form of ATP, the tree moves to the final stage of the forge. Out in the fluid surrounding the thylakoids, the plant opens microscopic pores on the underside of its leaves to inhale carbon dioxide gas from the air. Using the newly forged ATP as a power source, the factory physically hammers these invisible gas molecules together, welding the carbon atoms into long, heavy, solid chains of glucose. The biological skyscraper has successfully performed the ultimate act of chemical alchemy. It has taken the invisible radiation of a star and the intangible gas of the atmosphere and physically forged them into the solid, heavy sugars needed to build the massive, towering fortress of wood. To feed the microscopic solar panels in the high canopy, the biological skyscraper demands a continuous, massive influx of raw water. Every single photon strike and every shattered oxygen atom requires a replacement water molecule to be instantly delivered to the chloroplast. For a human engineer, moving thousands of gallons of heavy liquid hundreds of feet straight up into the air is a massive logistical hurdle. It requires heavy-duty industrial pumps, vast amounts of electrical fuel, and a pressurized, sealed plumbing network. The tree possesses no electrical grid, no moving mechanical parts, and absolutely no biological heart to pump the fluid. Yet, it effortlessly lifts tons of water from the deep subterranean soil all the way to the tips of its highest leaves. It achieves this impossible feat by abandoning active biological pumping and relying entirely on the extreme, violent physics of thermodynamics and molecular tension. The physical plumbing network of the tree is called the xylem. As the biological 3D printer of the tree, the cambium generates new cells. It dedicates a massive portion of them strictly for water transport. But a living, squishy cell filled with cytoplasm cannot efficiently move water. The cellular machinery is in the way. To solve this, the tree engages in a methodical process of programmed cellular death. It heavily reinforces the walls of these newly printed cells with rigid lignin and then intentionally kills them. The internal biological machinery completely dissolves, leaving behind nothing but millions of hollow, heavily armored, microscopic tubes stacked end to end. This is the xylem network. It is not living tissue. It is a vast, dead, wooden capillary system reaching from the deepest root tips to the highest leaves. But a pipe is useless without a pump. The true mechanical engine driving this massive upward flow is not located in the roots. It is located in the sky. On the underside of every leaf are thousands of microscopic, mechanically operated mouths called stomata. When the sun rises, the tree physically forces these mouths open to inhale the atmospheric carbon dioxide required for its solar forges. But opening a wet, pressurized interior to the dry, sun-baked atmosphere comes with a violent physical consequence. The water inside the leaf instantly evaporates and is sucked out into the dry air. This process of evaporation is called transpiration, and it is the invisible, thermodynamic engine of the entire forest. As a single water molecule evaporates and leaves the microscopic mouth, it creates a tiny, localized physical void inside the leaf. Because of the unique chemical architecture of water, this void does not remain empty. A water molecule is highly polarized. Its oxygen atom carries a slight negative magnetic charge, and its two hydrogen atoms carry a slight positive magnetic charge. In the microscopic confines of the xylem pipe, these opposing charges act like highly powerful electromagnets. Every single water molecule is violently attracted to the molecules surrounding it, snapping together in a tight, inescapable chemical grip known as a hydrogen bond. This molecular grip is called cohesion. Because every molecule in the pipe is physically holding onto the molecule directly beneath it, the water does not behave like a sloshing liquid. It behaves exactly like a solid, continuous steel cable. When the evaporating water molecule at the very top of the tree is violently pulled out into the atmosphere, it physically drags the molecule beneath it up into its place. That molecule drags the next one and the next one, setting off a continuous, mechanical chain reaction that travels hundreds of feet straight down the trunk and deep into the subterranean roots. The sun literally reaches down and physically pulls the entire liquid column upward, but the sheer weight of a towering column of water is staggering. Gravity is relentlessly trying to drag that massive liquid cable back down to the earth. To prevent the heavy column from violently slipping backward and crashing down to the roots, the tree relies on a second physical phenomenon called adhesion. The charged water molecules are not just attracted to each other, they are magnetically attracted to the rigid, lignified walls of the dead xylem pipes. They physically grab onto the sides of the microscopic tubes, anchoring the massive weight of the water column directly to the wooden skeleton of the tree. Because the sun is pulling the water violently upward and gravity is pulling it violently downward, the liquid trapped inside the xylem is subjected to immense physical stretching. The water is stretched so hard that it physically enters a state of extreme negative pressure. It is no longer being pushed, it is being violently ripped apart from both ends. The entire survival of the biological skyscraper relies on the microscopic tensile strength of these hydrogen bonds, holding firm under thousands of pounds of sheer physical stress. While the dead water pipes are a marvel of passive physics, relying entirely on the extreme, violent tension of hydrogen bonds to drag liquid skyward, a biological skyscraper cannot survive on water alone. The microscopic solar forges in the high canopy are relentlessly manufacturing heavy, solid chains of glucose. This vital, energetic fuel must be transported out of the leaves and delivered to the living tissue across the entire fortress, especially the deep subterranean roots, which are permanently locked in absolute darkness and would rapidly starve without a constant supply of energy. Moving heavy, highly viscous sugar sap requires a completely different mechanical architecture than pulling water. You cannot pull a thick syrup with passive tension. The chemical bonds would simply snap under the immense friction and the dead weight of the fluid. Instead, the tree must forcefully push the sap. To achieve this, the fortress abandons the dead, hollow pipes of the water network and constructs a parallel, entirely living hydraulic system. This secondary plumbing network is called the phloem. The construction of this living pipeline is a bizarre biological compromise. To create a clear, unobstructed channel for the thick sap to flow, the individual cells that make up the pipeline, known scientifically as sieve tube elements, must be completely hollowed out. The tree forcefully dismantles and dissolves the cell's nucleus, its ribosomes, and its central storage tanks. The interior is swept entirely clean, leaving nothing but a continuous, microscopic tunnel. However, unlike the dead wooden pipes of the water network, these sugar pipes must remain biologically alive to actively manage the fluid pressure. A biological cell that lacks a nucleus and ribosomes is functionally brain dead and physically incapable of repairing its own damaged structures. To keep these hollowed-out pipeline cells functioning, the tree pairs every single one of them with a fully equipped support unit called a companion cell. The companion cell acts as a dedicated life support system and a localized biological engine. It is heavily packed with energy-producing mitochondria, and it physically connects itself to the hollow pipeline cell via microscopic biological tunnels. When the solar panels in the leaf finish forging glucose, the mechanical loading process begins. The companion cells use raw biological energy to physically grab the sugar molecules and forcefully pump them into the top of the hollow sieve tubes. This is an active, violent biological process. The companion cells are stuffing massive amounts of heavy sugar into a tightly confined microscopic space, fighting directly against the natural laws of chemical diffusion to create a hyper-concentrated reservoir of fuel. As the sugar concentration inside the top of the living pipe skyrockets, a secondary physical phenomenon is immediately triggered. Just a microscopic fraction of a millimeter away lies the dead water pipe, completely filled with rushing liquid. Because the sugar pipe is now hyper-loaded with glucose, the inescapable laws of osmosis take over. Water molecules are violently pulled out of the dead pipes and dragged directly through the cellular membranes into the living pipes, desperately attempting to dilute the massive concentration of sugar. This sudden, violent influx of water into a sealed, living pipeline generates an immense physical consequence. The fluid inside the pipeline is completely trapped by the rigid outer cellulose walls of the cell. As more and more water forcefully rushes in to balance the sugar, the internal hydrostatic pressure skyrockets. The soft, living cell becomes an intensely pressurized biological cannon. The localized physical pressure at the top of the tree reaches terrifying levels, easily exceeding the physical pressure contained inside a heavy-duty commercial truck tire. The sheer physical force of this hydrostatic pressure is perfectly demonstrated by the insects that attempt to feed on the tree. When a specialized insect, like an aphid, lands on the bark to steal the sugar, it does not physically suck the sap out of the tree. The insect simply hammers its microscopic, needle-like mouthpart directly into the living pipe. Because the internal hydrostatic pressure of the tree is so violently high, the thick sugar sap is physically blasted up through the insect's mouth, straight through its digestive tract, and forcefully ejected out the other end of its body. The insect is essentially tapping a highly pressurized biological fire hydrant, completely at the mercy of the tree's internal fluid dynamics. Because the bottom of the tree, down in the subterranean roots, is constantly consuming the sugar, the fluid pressure at the base of the living network is significantly lower. The fundamental laws of fluid dynamics dictate that high pressure must relentlessly flow toward low pressure. The immense, localized hydrostatic pressure at the top of the tree physically crushes down on the heavy, viscous sugar sap, forcefully driving the thick liquid down the towering trunk and deep into the root system. This is a pressurized, positive displacement biological pump operating completely without a mechanical heart. While the dead, wooden pipes are violently stretching water upward under extreme negative tension, the living, pressurized pipes are simultaneously driving thick, heavy syrup downward under massive positive pressure. The two opposing hydraulic systems run completely parallel to one another, perfectly balancing the extreme fluid dynamics required to keep the multi-ton biological skyscraper alive and fully fueled. To stand upright against the crushing weight of gravity, A towering biological skyscraper must possess an internal architecture capable of withstanding immense physical forces. Pushing heavy, viscous sap down to the roots and violently pulling water up to the canopy is a masterclass in fluid dynamics. But fluid alone cannot provide structural rigidity. If the towering organism relied solely on pressurized liquid to hold itself upright, a single severe drought or a violently high wind would cause the entire multi-ton fortress to catastrophically buckle and collapse. The organism requires a physical skeleton, a hardened composite material capable of resisting both tension and compression. It must build wood. The construction of this biological armor begins with the exhaust of the solar forges. The massive quantities of glucose manufactured in the high canopy are not just burned as active energy, they are physically repurposed as the primary building blocks for the tree's physical skeleton. The cellular machinery grabs thousands of individual glucose molecules and chemically welds them together end to end, forging massive linear chains. These chains are called cellulose. By itself, a single strand of cellulose is microscopic and highly fragile, but the tree does not use single strands. It tightly bundles dozens of these chains together, twisting them into highly organized, microscopic cables known as microfibrils. These cellulose cables are incredibly strong under tension. They act exactly like the braided steel cables used in modern suspension bridges. Because of the specific positive and negative electrical charges along the glucose molecules, the chains chemically lock together, creating a structure that physically resists being stretched or torn apart. However, a steel cable has a fatal mechanical flaw. While it is incredibly strong when pulled, it possesses absolutely no compressive strength. If you attempt to stand a steel cable on its end and push down on it, it instantly bends and collapses. A skyscraper built entirely out of flexible cellulose cables would simply flop over under its own colossal weight. To solve this structural crisis, the tree must invent biological concrete. It must manufacture a secondary chemical component to physically lock the flexible cellulose cables into a rigid, load-bearing pillar. This secondary component is a heavy, highly complex polymer called lignin. Unlike the perfectly ordered, linear chains of cellulose, lignin is chemically chaotic. It is a massive, sprawling, three-dimensional web of heavy carbon rings. When a newly printed structural cell is ready to be hardened into permanent wood, the tree violently pumps raw lignin into the cell wall. The heavy lignin molecules flow into the microscopic gaps between the flexible cellulose cables. Once inside, the lignin physically hardens, expanding and chemically welding itself to the cellulose. It violently displaces the water inside the cell wall, completely entombing the flexible cables in a rigid, waterproof, biological resin. This precise combination of flexible cellulose cables embedded inside rigid, hardened lignin creates a structural composite material that perfectly mirrors the mechanics of reinforced concrete. The cellulose provides the tensile strength, preventing the tree from snapping when it violently bends in a hurricane, while the lignin provides the compressive strength, preventing the immense, multi-ton weight of the canopy from physically crushing the trunk. This process of lignification is permanent. Once the biological concrete sets, the tree intentionally kills the living machinery inside the cell, leaving behind a completely hollow, heavily armored structural brick. Ring by ring, year after year, the tree physically locks millions of tons of carbon, pulled directly from the invisible atmosphere into this solid, indestructible physical vault. As the biological skyscraper continues to expand outward, printing new rings of armor every single year, the physical logistics of maintaining the entire structure begin to shift. The outer rings of this wooden skeleton, the sapwood, are actively utilized for the violent upward pulling of water, but the deeper, older rings closer to the center of the trunk are eventually retired from active plumbing duty. The tree forcefully plugs these older, inner pipes with heavily toxic chemical resins and dense crystalline structures, completely sealing them off from the flow of water. This sealed, deeply buried core becomes the heartwood. It is the purest expression of the carbon vault. Because it is thoroughly saturated with hardened resins and physically locked away from oxygen and moisture, the heartwood becomes incredibly dense and highly resistant to biological decay. It no longer functions as a fluid transport network. It exists solely as a massive, dead, centralized pillar of sheer structural support. The absolute physical density of this dead core acts as a heavily weighted ballast, anchoring the center of gravity low to the ground and providing the immense physical leverage required to keep the sprawling, heavy branches of the canopy suspended in the air. The tree is quite literally standing on the heavily embalmed, fossilized remains of its own youth. While the towering carbon vault of the trunk provides the necessary compressive strength to support the immense weight of the canopy, a skyscraper is only as stable as its foundation. A multi-ton biological structure, reaching hundreds of feet into the atmosphere, acts as a colossal, physical lever. When hurricane-force winds violently push against the expansive surface area of the leaves and branches, they generate an astronomical amount of mechanical torque at the base of the trunk. If the biological fortress were simply resting on the surface of the Earth, this rotational force would instantly snap the trunk or rip the entire structure completely out of the ground. To counteract this violent atmospheric leverage, the tree must engineer a subterranean mirror image of itself. It must construct a sprawling, heavily fortified anchoring system that physically binds the skyscraper to the bedrock. This is the root system, and it is a masterpiece of geotechnical engineering. When a new root first attempts to penetrate the soil, it faces a severe mechanical hurdle. Soil is incredibly dense, heavily compacted, and filled with solid rock. The delicate, living cells at the very tip of the growing root are far too soft to simply push their way through this abrasive matrix. To solve this, the tree deploys a specialized, heavily armored structure called the root cap. The root cap acts as a biological drill bit. It is a thick, disposable shield of cells that covers the fragile, actively dividing tissue just behind it. As the root drives forward into the darkness, the abrasive soil violently tears the cells of the root cap away. But the tree is constantly printing new sacrificial cells from behind, continually replacing the armor as fast as it is shredded. To further reduce the immense physical friction of the earth, the outer layers of the root cap constantly secrete a highly viscous, biological grease called mucilage. This slime chemically lubricates the soil directly in front of the root, allowing the mechanical drill bit to slip between tightly packed grains of sand and clay. However, lubrication and armor are useless without a driving force. The root possesses no muscles to dig. Instead, it relies on the exact same hydraulic engine that keeps the leaves inflated, which is turgor pressure. By violently pumping water into the newly formed cells just behind the root cap, the tree causes those cells to rapidly expand and elongate. Because the cells are encased in rigid cellulose boxes, they can only expand in one physical direction, forward. This rapid, unidirectional expansion transforms the microscopic root tip into a pressurized hydraulic ram. The localized physical force generated by these expanding cells is staggering. It is strong enough to physically shatter subterranean stones, pry open microfractures in solid granite, and relentlessly drive the root network deeper into the earth. Once the root has successfully wedged itself into a new pocket of soil, its mechanical objective completely shifts from penetration to stabilization. The smooth, lubricated surface of the root tip offers absolutely no physical grip. To anchor itself, the root rapidly deploys millions of microscopic, thread-like extensions called root hairs. These hairs aggressively grow outward, squeezing into the microscopic voids between individual soil particles. By maximizing its physical contact with the earth, the root network generates a massive amount of surface friction. The tree is literally gripping the dirt at a microscopic level. As the biological skyscraper grows larger and the atmospheric torque on the canopy increases, these delicate, gripping roots must be upgraded into heavy-duty structural anchors. The tree achieves this by mirroring the exact same process of lignification used to build the trunk. It floods the older roots with heavy lignin, intentionally killing the internal tissue and turning the subterranean network into solid, hardened wood. This creates a dual anchor architecture. Thick, heavy taproots drive straight down like massive structural pilings, exploiting the deep friction of the subsoil. Simultaneously, a vast network of rigid, lateral roots spreads horizontally just beneath the surface. These horizontal roots act exactly like the tensioned guy wires on a radio tower. When the wind forcefully pushes the tree in one direction, the heavy lateral roots on the opposite side are pulled violently upward. Because they are securely entangled with thousands of pounds of densely packed earth, they physically resist the lift, flawlessly neutralizing the torque and locking the biological fortress safely against the planet. The biological skyscraper has successfully anchored itself to the bedrock and built a towering, pressurized water network. However, securing a physical grip on the earth does not solve the fundamental problem of chemical starvation. The massive solar forges in the canopy require specific raw materials to build chlorophyll and specialized proteins. They desperately need heavy elements, primarily nitrogen and phosphorus. While the soil is packed with these essential minerals, they are often locked inside microscopic pores within solid rock or bound tightly in decaying organic matter. The tree's roots, even the finest root hairs, are simply too massive and physically blunt to extract them. To acquire these inaccessible heavy elements, the tree must outsource its subterranean mining operations. It does this by forging a violent, physical alliance with an entirely different biological kingdom. It connects its root system to the fungal mycelium, creating the mycorrhizal network. A fungus operates under completely different physical constraints than a plant. It does not build thick, armored walls of wood. Instead, it expands through the earth as a sprawling web of microscopic, single-cell wide tubes known as hyphae. Because a single hyphal tube is infinitely thinner than the smallest tree root, it acts as a microscopic mining drill. Driven by localized hydrostatic pressure, the fungal tube physically forces its way into the microscopic crevices of solid granite and wraps itself intimately around individual grains of sand. Once wedged inside these impossibly tight spaces, the fungus deploys chemical artillery. It secretes highly concentrated organic acids directly onto the rock. These acids physically dissolve the mineral matrix, forcefully stripping away the bound phosphorus and nitrogen atoms. The fungus then pulls these free elements into its own pressurized plumbing network. But the fungus faces a critical energetic limitation. Because it lives entirely in the absolute darkness of the subterranean world, it possesses no solar panels. It cannot photosynthesize. It has vast stockpiles of mined heavy elements, but absolutely no sugar to fuel its own survival. The tree, conversely, is overflowing with sugar manufactured in the canopy, but is starving for heavy elements. The solution is a brutal, physical fusion of the two organisms. When a fungal hyphae encounters a young tree root in the dark soil, it does not passively sit next to it. It aggressively attacks the root. For ectomycorrhizal fungi, the hyphae physically weave themselves into a dense, restrictive sheath around the exterior of the root tip. They then forcefully push their way inward, wedging themselves violently between the individual plant cells of the root's outer cortex. They create a highly complex, microscopic maze of fungal tissue, completely embedded within the tree's architecture, known as the Hartig net. For endomycorrhizal fungi, the invasion is even more mechanically intrusive. The fungal tube releases specific enzymes to burn a microscopic hole straight through the rigid cellulose armor of the tree's root cell. The fungus violently pushes itself inside the plant cell. However, it does not breach the final, flexible inner membrane. Instead, it pushes against it, forcing the membrane to stretch and fold around the invading fungal tube like a microscopic glove. Inside the tree cell, the fungus physically branches out into a highly complex, tree-like structure, an arbuscule. This violent penetration is not an infection, it is the construction of a high-efficiency biological trading floor. By pushing so deeply and intricately into the plant tissue, the fungus maximizes the physical surface area where the two organisms touch. Across this microscopic boundary, the physical exchange begins. The tree uses active biological pumps to forcefully push its heavy, viscous sugar sap out of its root cells and directly into the waiting fungus. Simultaneously, the fungus uses its own mechanical pressure to pump the dissolved phosphorus and nitrogen out of its hyphae and into the tree. Through this physical fusion, the tree effectively expands its root system by thousands of miles. The biological skyscraper is no longer an isolated tower. It is physically hardwired into a sprawling subterranean grid, tethered mechanically to the surrounding earth and drawing raw power from a vast, invisible fungal engine. Animals possess a highly advantageous mechanical response to physical trauma. They can run away. When a biological fortress is under siege, it is permanently bolted to the bedrock. It cannot retreat, and it possesses no circulating white blood cells to hunt down an invader. To human eyes, a tree being slowly consumed by a swarm of insect larvae appears as a completely passive victim. But inside the pressurized living network, the tree is actively orchestrating a violent, highly targeted chemical counterattack. The first step in this defense is the physical detection of a perimeter breach. When a caterpillar lands on a leaf and begins to violently chew through the waxy cuticle, it is doing more than just removing tissue. The mechanical shearing of the mandibles against the rigid cellulose walls generates specific acoustic vibrations. Furthermore, the insect inevitably leaves behind traces of its own saliva, a complex mixture of biological enzymes. The tree's surviving cells immediately detect this highly specific chemical signature and the acoustic trauma of the chewing. The moment the mandibles slice through the rigid cellulose, the physical pressure inside the localized cells violently drops. This catastrophic loss of turgor pressure acts as an immediate mechanical tripwire. The localized cells at the site of the wound physically rupture and release a flood of specialized signaling molecules. The most critical of these are glutamate and calcium ions. Because the tree lacks a centralized nervous system, it must use its pressurized living plumbing network to transmit the alarm. The calcium ions trigger a cascading wave of electrical depolarization. Microscopic protein gates embedded in the cellular membranes violently snap open, allowing charged ions to flood the space before mechanically slamming shut again. This physical wave of opening and closing gates ripples across the living tissue. The electrical signal surges out of the damaged leaf and travels rapidly down the living, pressurized pipes at staggering speeds. As this electrical wave crashes into healthy, undamaged leaves across the canopy, it acts as a localized trigger. The biological 3D printers inside these healthy cells immediately shift their manufacturing focus. They stop printing the structural components of wood and the enzymes for photosynthesis. Instead, they rapidly spool up the production of heavy-duty chemical artillery. The primary weapons in this arsenal are secondary metabolites, complex, highly toxic chemical compounds that serve absolutely no role in the normal growth or fluid dynamics of the tree. One of the most common and physically devastating of these weapons is a class of chemicals known as tannins. When the tree floods its leaves with newly manufactured tannins, it is laying a microscopic physical trap for the invading insect. Tannins are large, highly astringent polyphenol molecules. When the caterpillar inevitably consumes the newly armed leaf, the tannins are drawn directly into the insect's highly alkaline digestive tract. Here, the physical thermodynamics of the trap are sprung. Tannins possess a violent chemical affinity for proteins. They aggressively bind to the caterpillar's own digestive enzymes, physically wrapping around them and violently clumping them together into hard, indigestible biological knots. The insect's digestive engine is physically seized. It can no longer break down the plant tissue it is consuming. With its gut securely locked by the tannins, the caterpillar simply starves to death with a full stomach. Simultaneously, the tree may synthesize an entirely different class of weapons known as alkaloids. These are precision neurological weapons. Unlike tannins, which physically jam the digestive tract, alkaloids are designed to breach the insect's central nervous system. When ingested, the molecules physically cross the gut barrier and aggressively bind to the neurological receptors in the insect's brain. They act as a localized neurotoxin, violently overstimulating the nerves until the insect goes into physical convulsions or complete paralysis. The tree has literally manufactured a custom-built nerve agent on demand. But the biological fortress does not stop at localized poisoning. If the physical trauma of the invasion is severe enough, the tree deploys a secondary, airborne warning system. The cells surrounding the wound rapidly manufacture and release highly volatile organic compounds, specialized gases that easily vaporize at ambient temperatures. As the pressurized gas physically escapes the microscopic pores of the damaged leaf, it is caught by the atmospheric wind. This gas is not just an alarm, it is a physical, airborne trigger. As the invisible chemical cloud drifts through the forest, it physically collides with the leaves of neighboring, completely undamaged trees. The surface receptors on these neighboring fortresses lock onto the volatile gas, instantly recognizing the chemical signature of an active siege. Even before a single insect touches their bark, these neighboring trees forcefully trigger their own internal calcium waves and proactively flood their canopies with toxic artillery. The solitary biological skyscraper has utilized fluid dynamics and atmospheric currents to arm an entire interconnected forest. The biological skyscraper possesses a sprawling network of living pipes and dead water channels, all heavily pressurized and rich with sugars. To the surrounding ecosystem, this towering structure is not just a plant, it is a massive, unprotected reservoir of calories and water. If the living tissue just beneath the surface were exposed to the outside world, it would be instantly devoured by insects, infected by fungal spores, and violently stripped of its moisture by the dry atmosphere. The chemical artillery is highly effective as a localized, reactive weapon, but a fortress cannot survive on reactive defenses alone. It requires a permanent, passive, and completely impenetrable outer shield. This is the bark citadel. To build this massive exterior wall, the tree deploys a secondary, heavily specialized biological 3D printer located just outside the living sugar pipes. This microscopic manufacturing layer is known as the cork cambium. Unlike the deep internal cambium, which prints the structural wood and plumbing, the cork cambium is tasked with a single, brutal mechanical objective: the mass production of sacrificial armor. When the cork cambium prints a new layer of cells, it does not design them for fluid transport or structural support. Instead, it forcefully injects the walls of these newly formed cells with a complex, highly repellent chemical polymer called suberin. Suberin is a waxy, heavily hydrophobic substance. It completely rejects water, acting exactly like an industrial-grade rubber sealant. Once the microscopic cell box is thoroughly flooded with suberin, the tree executes its standard manufacturing protocol for armor. It deliberately starves the living machinery inside the cell, killing it completely. The internal fluids violently evaporate or are reclaimed by the tree, leaving behind billions of microscopic, hollow, waxy boxes, completely filled with dead air. As the cork cambium relentlessly prints layer after layer of these dead cells, pushing the older layers outward, the tree creates a massive, heavily stratified physical barrier. This barrier of dead, air-filled cork cells serves as a masterpiece of thermodynamic engineering. In physics, trapped, stagnant air is one of the most effective thermal insulators in the universe. During the brutal extremes of deep winter, the ambient atmospheric temperature plunges far below freezing. If the water inside the living plumbing network of the tree were to freeze solid, the expanding ice crystals would violently shatter the rigid cellulose walls from the inside out, causing catastrophic structural failure. The thick layer of cork physically intercepts the plunging temperatures, slowing the thermodynamic transfer of heat so drastically that the internal plumbing network remains safely insulated and fluid. This exact same thermodynamic shield operates in reverse during a catastrophic forest fire. When a localized fire sweeps through the underbrush, the external temperatures skyrocket to hundreds of degrees. The outer layers of the dead bark will physically scorch and burn, but the microscopic pockets of dead air prevent the extreme kinetic heat from penetrating deep into the trunk. The heavily suberized cork absorbs the thermal trauma, completely shielding the delicate, living cambium printer located just millimeters beneath the surface. Beyond thermal physics, the suberin-infused bark acts as an absolute physical barricade against biological invaders. When a fungal spore lands on the exterior of the tree, it attempts to excrete liquid, acidic enzymes to dissolve the plant tissue. But because the suberin is heavily hydrophobic, the liquid enzymes simply bead up and roll away, completely unable to gain chemical traction. When a boring insect attempts to drill into the trunk, it must physically chew through inches of tough, nutrient-void, dead material. The sheer mechanical exhaustion of chewing through the cork often kills or deters the insect long before it ever reaches the sweet, pressurized sugar pipes hidden below. However, wrapping the entire biological skyscraper in an airtight, waterproof layer of rubberized armor creates a lethal mechanical paradox. The living cells of the inner bark and the cambium are trapped behind this impenetrable wall. Because they are alive, they must continuously burn fuel to survive, a process that requires a constant influx of atmospheric oxygen and the steady venting of waste carbon dioxide. If the cork shield is perfectly sealed, the living tissue beneath it will violently suffocate. To solve this, the tree engineers highly precise, localized structural flaws in the armor. These microscopic exhaust vents are called lenticels. They are specific, porous patches where the cork cells are printed loosely, creating a tangled, physical maze of microscopic gaps. These gaps are large enough to allow the free, thermodynamic diffusion of oxygen and carbon dioxide gases through the armor, but physically narrow and complex enough to completely block the entry of fungal spores and invasive insects. The fortress remains fully sealed against physical and thermodynamic trauma, while still utilizing these heavily guarded, microscopic breathing ports to keep its internal siege engines alive and functioning. Despite the heavily suberized armor of the outer bark, the mechanical failure of the exterior shield is an absolute physical certainty. A towering biological skyscraper is constantly subjected to catastrophic external trauma. High-velocity winds forcefully snap heavy branches. Lightning strikes instantly boil the internal water to violently blow the bark off the trunk, and heavy-duty boring insects relentlessly drill through the defensive cork. When a breach occurs, the highly pressurized internal plumbing networks are instantly exposed to the dry atmosphere and the microscopic spores of parasitic fungi. An animal responds to a deep physical wound by regenerating the damaged cells and physically replacing the tissue. A tree operates on a completely different mechanical paradigm. It cannot heal, it can only seal and entomb. The immediate, violent response to a physical breach is the deployment of a heavily pressurized biological sealant. Scattered throughout the living tissue and the outer rings of the wood are specialized microscopic pipelines known as resin ducts. These ducts are not designed for the transport of water or sugar. They are highly pressurized containment vessels completely filled with a thick, violently toxic, and extremely viscous chemical fluid called resin. When a boring beetle physically chews its way through the outer bark and breaches the living tissue, it inevitably severs one of these pressurized ducts. The mechanical result is instantaneous. Because the internal hydrostatic pressure of the duct is vastly higher than the atmospheric pressure outside, the thick resin explosively floods the microscopic tunnel. The invading insect is instantly hit with a tidal wave of biological sealant. This resin is an engineering marvel of physical defense. It is primarily composed of heavy, sticky resin acids dissolved in highly volatile liquid compounds called terpenes. The terpenes act as a harsh chemical solvent. They violently attack the rigid exoskeleton of the insect and flood its respiratory spiracles, the microscopic holes it uses to breathe, causing immediate chemical suffocation. But the true mechanical power of the resin is activated by the surrounding atmosphere. As the highly volatile terpenes rapidly evaporate into the open air, the remaining heavy acids are left behind. Stripped of their liquid solvent, these acids undergo a massive physical polymerization. They chemically lock together, transitioning the fluid from a sticky syrup into a solid, hardened mass of biological amber. The insect is not merely killed, it is permanently entombed inside a solid, waterproof plug that completely seals the physical breach from the outside world. However, a localized surface plug is completely insufficient to stop the microscopic spread of a fungal infection that has already slipped inside the vascular system. Because the dead water pipes are hollow, highly interconnected, and completely filled with moisture, a fungal spore can rapidly use the tree's own plumbing network as an unobstructed highway to spread rot throughout the entire skyscraper. To stop this internal systemic failure, the tree must physically isolate the infected sector. It executes a brutal strategy of internal compartmentalization. The tree immediately sacrifices the damaged plumbing. Surrounding the dead water pipes are specialized, living parenchyma cells. When these living cells detect the chemical signature of invading fungal hyphae, they execute a violent mechanical expansion. The living cell forcefully pushes its own flexible membrane directly through the microscopic pits in the rigid wall of the dead water pipe. It inflates inside the hollow tube exactly like a highly pressurized biological balloon. This structure is called a tylose. Thousands of these microscopic balloons inflate simultaneously, violently swelling until they completely choke off the dead pipe, creating an absolute physical barricade that stops the flow of water and halts the spread of the fungus. With the internal plumbing physically blocked and the exterior wound plugged with hardened resin, the biological 3D printer, the cambium, shifts its manufacturing protocol. It temporarily stops printing organized rings of structural wood. Instead, it begins rapidly extruding a chaotic, highly energized mass of undifferentiated cells known as callus tissue. This callus tissue physically rolls over the edge of the gaping wound, slowly creeping inward year after year. It acts as a heavy, biological scar, laying down massive, thick layers of heavily lignified wood to permanently cap the injury. The tree does not replace the wood that was destroyed by the lightning strike or the fungal rot. It simply entombs the dead, rotting sector within a completely sealed, airtight, and chemically toxic vault, building a brand new, physically sound layer of armor directly over the top of the graveyard. The biological fortress survives by continuously burying its own structural failures beneath relentless layers of new growth. The biological fortress faces an annual, catastrophic physical threat. As the planet's axial tilt physically angles the hemisphere away from the sun, the ambient atmospheric temperature rapidly plunges toward the freezing point of water. Inside the towering structure, millions of gallons of liquid are trapped within microscopic, rigid cellulose boxes and hollow wooden pipes. The fundamental thermodynamics of water dictate that as it freezes into a solid crystalline matrix, it violently expands. If the water inside the living plumbing network were allowed to undergo this phase transition, the expanding ice crystals would act as microscopic biological bombs. They would physically shatter the rigid cellular walls from the inside out, completely destroying the structural integrity of the entire organism. To survive this annual thermodynamic assault, the tree must execute a highly coordinated, mechanical shutdown of its most vital systems. The first severe vulnerability is the massive canopy of solar panels. Broad leaves are incredibly thin and completely filled with moisture, making them physically impossible to insulate against a deep freeze. Furthermore, if the stomata, the microscopic mechanical mouths on the leaves, remained open during the dry winter air, they would continue to violently pull water up from the roots, while the soil itself was frozen solid. The extreme tension inside the dead wooden pipes would instantly snap, causing massive, lethal cavitations that would permanently destroy the plumbing. The tree must proactively amputate its own canopy. This mechanical process begins with a chemical signal that entirely halts the production of chlorophyll. As the highly unstable green pigment physically degrades under the solar radiation, the heavy, residual chemical compounds, the yellow and red pigments that were constantly hidden underneath, are temporarily exposed before the leaf finally dies. Simultaneously, at the exact microscopic point where the stem of the leaf connects to the heavy wooden branch, the tree constructs a specialized, highly localized ring of cells called the abscission zone. This zone acts as a biological scalpel. The cells within this microscopic ring are actively flooded with localized enzymes that physically dissolve the rigid chemical glue holding their cell walls together. As the structural bonds are systematically severed, the cells violently swell with water, pushing against each other until the physical tension snaps the connection entirely. The leaf is mechanically disconnected from the living vascular system and falls to the earth, entirely driven by gravity. But severing a biological connection leaves thousands of microscopic plumbing pipes completely open to the harsh atmosphere. Before the leaf even hits the ground, the tree forcefully injects the raw, exposed wound with heavily suberized cork cells, chemically sealing the breach and completely locking the internal moisture inside the heavily armored fortress. With the solar panels discarded and the plumbing securely sealed, the tree must now address the millions of gallons of water still trapped inside its trunk and root system. It cannot physically drain this water, so it must completely alter the fundamental thermodynamics of the fluid. The tree initiates a massive, internal chemical refinery process. Throughout the summer, the tree stored its excess solar energy in the form of heavy, solid starch molecules deep inside the roots. Now, it violently breaks those solid starches back down into highly concentrated, soluble sugars and forcefully pumps them directly into the living cells. This hyperconcentration of sugar physically changes the freezing dynamics of the water. By packing the fluid with heavy solute molecules, The tree drastically lowers the freezing point of the liquid, acting exactly like an industrial, heavy-duty antifreeze poured directly into a mechanical engine. In the most extreme, sub-zero climates, the tree takes this thermodynamic manipulation one step further. It forces the water inside its cells to undergo a physical process known as vitrification. By precisely managing the internal hydrostatic pressure and the hyperconcentration of complex sugars, the tree prevents the water molecules from physically aligning into sharp, expanding ice crystals. Instead, as the ambient temperature plummets, the liquid violently thickens into an incredibly dense, amorphous biological glass. The internal cellular machinery is completely suspended in a solid frozen state, but because the fluid never crystallized and expanded, the rigid cell walls do not shatter. The biological skyscraper stands completely dead to the outside observer, its internal plumbing halted, its solar forges amputated, and its cellular engine chemically vitrified into solid glass, perfectly suspended in time until the thermal radiation of the spring sun physically melts the fortress back into a state of violent hydraulic motion. For a human engineer to construct a towering skyscraper, they must rely on highly precise mechanical tools, such as plumb lines and fluid levels, to ensure the physical architecture is perfectly aligned with the Earth's gravitational pull. If a massive structure leans even a fraction of a degree off its vertical axis, the asymmetrical distribution of millions of tons of weight will eventually cause a catastrophic mechanical collapse. The biological fortress faces this exact same physical threat, but it must solve the engineering problem in absolute blindness. When a heavy seed first falls from the canopy and violently impacts the soil, it tumbles chaotically. It is just as likely to land completely upside down as it is right side up. As the hard outer shell cracks and the new biological machinery begins to forcefully deploy in the absolute darkness of the subterranean Earth, the organism possesses no eyes, no central nervous system, and no conscious awareness of its physical orientation. Yet, the newly printed roots will flawlessly drive straight down into the bedrock, and the fragile stem will violently push straight up toward the atmosphere. To achieve this flawless spatial orientation, the tree relies on a microscopic, highly sensitive mechanical sensor known as a statocyte. These specialized sensory cells are completely localized. They are packed tightly into the very tip of the heavy armored root cap, the sacrificial biological drill bit we explored earlier, and within a specific, heavily fortified sheath of tissue surrounding the young stem. Inside these microscopic, fluid-filled boxes, the tree constructs the biological equivalent of a plumb line. A standard plant cell is filled with a watery cytoplasm that houses the biological machinery, but the interior of a statocyte contains something much heavier. The tree actively manufactures dozens of incredibly dense, microscopic boulders known as statoliths. These are highly concentrated, tightly packed geometric spheres of solid starch. Because starch is physically much denser than the surrounding cellular fluid, these microscopic boulders are entirely at the mercy of physical gravity. If a severe storm violently blows a young sapling over, pinning its trunk parallel to the ground, the statocytes are instantly tilted on their side. The heavy statolith boulders physically lose their footing. Pulled by the inescapable gravity of the planet, they violently sink through the viscous fluid of the cell, crashing down until they physically collide with the new bottom wall of the microscopic box. This is not a passive collision. The interior of the cell wall is heavily lined with an incredibly complex, highly tensioned web of structural proteins, the cytoskeleton, and a sprawling network of biological tubing, the endoplasmic reticulum. When the heavy starch boulders violently crash into this delicate internal webbing, the sheer physical weight of the statoliths generates intense mechanical pressure. They physically crush and stretch the microscopic membranes beneath them. This mechanical deformation is the exact trigger the biological fortress needs. The physical stretching of the membrane violently snaps open specialized microscopic gates, allowing a sudden, localized flood of calcium ions to completely alter the electrical charge of the cell's bottom floor. The physical weight of gravity has been flawlessly translated into an electrical alarm. The biological 3D printers immediately respond to this electrical surge by aggressively relocating a highly potent microscopic chemical called auxin. Auxin is a heavy plant hormone that dictates the physical architecture of the cell walls. When the statoliths trigger the alarm on the bottom floor of the horizontal root, the root aggressively pumps massive quantities of auxin directly into the cells on its lower half. In the root system, a hyperconcentration of auxin acts as a powerful mechanical brake. It physically prevents the biological machinery from loosening the rigid cellulose fibers. Because the cells on the top half of the horizontal root have very little auxin, their cellulose walls remain flexible. The localized hydrostatic engine, the turgor pressure, violently forces the top cells to expand and elongate, while the bottom cells are locked completely rigid. With the top physically lengthening and the bottom remaining stagnant, the solid wooden structure mechanically warps, forcefully bending the entire root system 90 degrees downward until it is driving straight back into the earth. In the stem of the tree, this exact same chemical machinery operates on completely inverted physical rules. When the statoliths in the fallen trunk sink and trigger the auxin flood to the bottom side of the stem, the auxin does not act as a brake. Instead, in the upper architecture of the fortress, the auxin acts as a violent accelerator. It chemically severs the structural crosslinks holding the rigid cellulose cables together, massively weakening the cell walls on the bottom half of the trunk. The immense turgor pressure immediately exploits this localized structural weakness, violently expanding the bottom cells while the top cells remain rigid. The entire massive, multi-ton trunk mechanically warps and bends 90 degrees upward, relentlessly fighting the torque until the biological plumb line is perfectly reset and the towering skyscraper is safely realigned with the sky. To understand the true scale of this biological engineering, we must pull back from the microscopic plumbing of a single trunk and view the organism not as an isolated skyscraper, but as a single piston within a continental-scale thermodynamic engine. When you place millions of these towering, heavily pressurized fortresses side by side, they cease to be individual organisms. They merge into a unified, physical terraforming machine that is powerful enough to actively dictate global weather patterns and chemically alter the atmosphere of the entire planet. The most immediate and physically violent impact of this collective machine is the manipulation of the planetary water cycle. As we established, a single biological skyscraper relies on the extreme negative tension of hydrogen bonds to drag heavy liquid from the deep subterranean bedrock up into the high canopy. But that water does not simply stay inside the leaf. Through the microscopic mechanical mouths, the stomata, the solar panels continuously vent this internal moisture out into the dry atmosphere as invisible water vapor. When you multiply this localized evaporation by billions of leaves across millions of trees, the sheer volume of water being forcefully injected into the sky is astronomical. A sprawling forest acts as an array of massive, heavy-duty hydraulic pumps, relentlessly sucking subterranean aquifers dry and blasting that liquid mass directly into the lower atmosphere. This continuous, violent ejection of moisture physically saturates the air, drastically altering the localized humidity and creating vast, invisible atmospheric rivers that flow directly above the canopy. But the forest does not just release water, it actively controls where that water goes. The physical mechanics of this atmospheric control are governed by the thermodynamics of condensation. In the open atmosphere, water vapor is highly energetic and chaotic. For it to cool down and condense back into heavy, liquid raindrops, it requires a physical anchor. The gaseous water molecules need a solid, microscopic surface to crash into and chemically grip. In a sterile atmosphere, water vapor will simply remain a gas. To force the atmosphere to drop its payload, the biological fortresses deploy their chemical refineries. The exact same highly volatile organic compounds, the reactive gases manufactured as airborne chemical artillery to warn neighboring trees of an insect siege, are violently vented into the sky in massive quantities. As these complex carbon molecules hit the upper atmosphere, they physically collide with ultraviolet solar radiation and highly reactive ozone. This cosmic collision violently oxidizes the chemical gases, transforming them into solid, microscopic, airborne particulates. These floating particulates act exactly like microscopic scaffolding. They are scientifically classified as cloud condensation nuclei. As the humid atmospheric river flows over the canopy, the chaotic water vapor physically crashes into these newly forged particulates. The water molecules chemically lock onto the solid surfaces, rapidly aggregating and building heavily pressurized droplets. The forest is quite literally seeding its own sky. It is manufacturing the exact physical architecture required to force the atmosphere to condense. By continuously blasting both raw water vapor and solid microscopic scaffolding into the air, the collective engine forcefully builds massive, localized storm clouds. When the physical weight of the condensed water droplets finally overcomes the upward thermodynamic draft of the air, gravity takes over. The water violently crashes back down to the earth, heavily soaking the subterranean soil and perfectly refilling the underground aquifers that the root networks are continuously draining. The biological fortress does not passively wait for the weather to happen. It actively manufactures its own rain to ensure its high-tension plumbing networks never run dry. Furthermore, this continuous, massive evaporation creates a localized thermodynamic vacuum. Because water vapor is a gas, its continuous addition to the atmosphere physically alters the air pressure above the canopy. As the water condenses into liquid rain, the local atmospheric volume violently shrinks, dropping the air pressure. This localized drop in pressure acts as a massive continental vacuum cleaner. It physically drags massive currents of moist, heavy air from the distant oceans deep into the interior of the continents to fill the void. This mechanical process, known as the biotic pump, It proves that the forest is the true physical engine, driving the global distribution of rainfall. When we look at a dense, sprawling forest, we are not looking at a quiet landscape. We are looking at a roaring, heavily pressurized industrial complex. It is a unified network of billions of dead wooden pipes, violently stretching water to its absolute breaking point. It is a synchronized array of microscopic solar forges, permanently locking atmospheric carbon into indestructible vaults of biological concrete. It is a subterranean grid of chemical miners, violently dissolving solid granite in the absolute dark. It is the ultimate triumph of mechanical engineering, built entirely out of sunlight, water, and dead cellular armor, permanently bolted to the bedrock and relentlessly terraforming the earth.